embark on an awe-inspiring journey to the farthest reaches of our solar system, where Pluto, a small but captivating icy world, continues to challenge our understanding and spark wonder. Once hailed as the 9th planet, Pluto has been reclassified as a dwarf planet, yet its mysteries and allure remain as powerful as ever. In this video, we'll uncover the secrets of this distant wanderer, exploring its icy landscapes, enigmatic atmosphere, peculiar orbit, and intriguing moons. We'll dive into the groundbreaking discoveries from the New Horizons mission that revealed Pluto's unexpected complexity and reflect on what this tiny world teaches us about the vast cosmos. Prepare to be immersed in the chill, the wonder, and the fascination of Pluto, a world that feels both alien and strangely familiar, pushing the boundaries of what we believe is possible in our solar system. I've always called Pluto the farthest wanderer, a poetic nod to its remote location and the enigma it represents in the vastness of space. Nestled in the Kuiper Belt, a distant region brimming with icy bodies beyond Neptune, Pluto orbits the Sun at an average distance of 5.9 billion kilometers, making it one of the most far-flung objects in our solar system. Discovered in 1930 by American astronomer Clyde Tombaugh at the Lowell Observatory, Pluto captured the world's imagination as the 9th planet for decades. However, in 2006, the International Astronomical Union redefined what constitutes a planet, reclassifying Pluto as a dwarf planet because it shares its orbit with other Kuiper Belt objects and hasn't cleared its path of debris. Measuring just 2,377 kilometers in diameter, smaller than Earth's moon and even some moons in our solar system, Pluto may be small, but its scientific importance is immense. Pluto's surface is a frozen tapestry of nitrogen, methane, and carbon monoxide ices, shimmering faintly under the dim sunlight that takes over 5 hours to reach it. This icy composition, combined with organic compounds called tholins, gives Pluto a reddish-brown hue, formed when ultraviolet light and cosmic rays interact with methane. These tholins are not just a visual curiosity, they're a chemical signature that links Pluto to the primordial materials of the solar system's formation 4.6 billion years ago. Unlike rocky planets like Earth or gas giants like Jupiter, Pluto's icy nature makes it a time capsule, preserving clues about the conditions that existed when the solar system was young. Its surface temperature averages a frigid 229 degrees Celsius, cold enough to keep its ices solid but dynamic enough to support geological activity, as later discoveries would reveal. Studying Pluto's composition is crucial because it offers a direct link to the building blocks of planets, helping scientists piece together the story of how our solar system came to be. Beyond its physical makeup, Pluto's place in the Kuiper Belt adds to its significance. The Kuiper Belt is a vast donut-shaped region populated by countless icy bodies, from tiny fragments to dwarf planets like Eris and Haumea. Pluto is one of the largest known objects in this region, making it a prime target for understanding the belt's diversity and evolution. Its discovery in 1930 marked the first glimpse into this distant frontier, and since then it has served as a gateway to exploring the outer solar system. For astronomers, Pluto is not just a single world, but a representative of a whole class of objects that could number in the trillions. By studying Pluto, we gain insights into the processes that shaped the Kuiper Belt, such as collisions, gravitational interactions, and the migration of planets like Neptune billions of years ago. Moreover, Pluto's story resonates culturally, as its reclassification sparked global debates about what defines a planet, reminding us that science is a dynamic process of discovery and redefinition. Pluto's atmosphere is a delicate, ephemeral veil, unlike anything else in the solar system, and its study has revealed a world far more dynamic than its distance might suggest. Composed primarily of nitrogen, with traces of methane and carbon monoxide, this atmosphere is extraordinarily thin, with a surface pressure about 100,000 times less than Earth's, comparable to the vacuum of deep space. Yet it is remarkably complex, existing only when Pluto is closer to the Sun during its highly elliptical 248-year orbit. When Pluto approaches its perihelion, about 4.4 billion kilometers from the Sun, solar heat sublimates the surface ices, turning them directly into gas and forming a tenuous atmosphere. Conversely, at its farthest point, around 7.4 billion kilometers, the cold causes these gases to freeze and collapse back onto the surface as frost, a cyclical process that stunned scientists when observed by the New Horizons spacecraft in 2015. This freeze-thaw cycle is a unique feature, making Pluto a natural laboratory for studying atmospheric dynamics on low-gravity, icy worlds. The atmosphere's structure is another surprise. Despite its thinness, it supports multiple layers of haze extending up to 200 kilometers above the surface. These hazes, formed by chemical reactions between methane and ultraviolet light or cosmic rays, create a bluish tint that gives Pluto an ethereal glow. The hazes are composed of complex organic molecules, including tholins, which settle onto the surface and contribute to its reddish hue. New Horizons detected at least a dozen distinct haze layers, each shaped by atmospheric winds and chemical processes, indicating a surprisingly active system. These winds, though gentle due to the low pressure, can sculpt surface features and distribute particles across the planet. The presence of such hazes also suggests that Pluto's atmosphere is constantly replenished as it loses gas to space due to its weak gravity, a process accelerated by the solar wind. Understanding Pluto's atmosphere is critical for several reasons. First, it provides insights into how volatile ices, nitrogen, methane, and carbon monoxide, behave under extreme conditions, a process relevant to other Kuiper Belt objects and distant exoplanets with similar compositions. For example, the dwarf planet Eris and some of Neptune's moons, like Triton, share icy surfaces that may support similar atmospheres. Second, the atmosphere's interaction with the surface offers clues about Pluto's geological activity. The sublimation of ices can create pressure differences that drive winds or even trigger minor surface changes, linking the atmosphere to the planet's evolving landscape. Finally, the presence of organic molecules in the atmosphere raises tantalizing questions about prebiotic chemistry. While Pluto is far too cold for life as we know it, the same chemical processes observed here could occur on warmer worlds, providing a stepping stone to understanding the origins of life elsewhere in the universe. The study of Pluto's atmosphere also has implications closer to home. Its sensitivity to solar distance mirrors how Earth's atmosphere responds to changes in solar radiation, albeit on a vastly different scale. By modeling Pluto's atmospheric collapse and reformation, scientists can refine their understanding of climate dynamics on planets with thin or seasonal atmospheres, including Mars or even hypothetical exoplanets. The data from New Horizons, including measurements of atmospheric escape rates, has helped confirm that Pluto loses about 10^23 molecules per second to space, a slow but steady process that shapes its long-term evolution. This atmospheric loss, combined with the haze formation, makes Pluto a key case study for planetary scientists seeking to understand how small bodies maintain or lose their atmospheres over billions of years, offering a glimpse into the delicate balance that governs planetary environments. The surface of Pluto is a geological marvel, a testament to a world far more active and dynamic than its remote location and small size would suggest. When NASA's New Horizons spacecraft flew by in 2015, it unveiled a landscape that shattered expectations, revealing a world of stunning diversity and complexity. Pluto's surface is a patchwork of terrains, ranging from towering mountains to vast, smooth plains, all sculpted from ices and shaped by processes that continue to intrigue scientists. The most iconic feature is Sputnik Planitia, a heart-shaped basin roughly 1,000 kilometers wide, part of the larger Tombaugh Regio. This heart is not just a visual landmark, it's a dynamic region filled with nitrogen ice that behaves like a glacier. Convection cells within Sputnik Planitia slowly churn the ice, driven by faint internal heat, possibly from radioactive decay in Pluto's rocky core. This process creates a pitted cellular pattern, resembling a cosmic honeycomb and indicating geological activity as recent as a few million years ago. Pluto's mountains, some rising up to 3,500 meters, are another surprise. These ranges, named Hillary Montes and Tenzing Montes after the Everest climbers, are composed of water ice which at Pluto's frigid 229 degrees Celsius is as hard as rock. These mountains are likely tectonic in origin, formed by stresses in the icy crust, possibly linked to the freezing of a subsurface ocean in Pluto's distant past. The rugged highlands surrounding Sputnik Planitia, such as the Cthulhu Macula, are darker and heavily cratered, suggesting an older surface coated with tholins, the reddish organic compounds formed by solar radiation. Yet, even these regions show signs of erosion and fracturing, hinting at ongoing surface renewal. The scarcity of craters across much of Pluto's surface is a critical clue, indicating that it has been reshaped within the last 100 million years, a blink in geological time, through processes like sublimation, convection, and possibly cryovolcanism. Cryovolcanoes, volcanoes that erupt volatile ices like ammonia or methane instead of molten rock, are among Pluto's most tantalizing features. Features like Wright Mons and Picard Mons, large mounds with central depressions, resemble volcanic structures, seen on icy moons like Triton or Europa. If confirmed, these cryovolcanoes would suggest that Pluto retains enough internal heat to drive such activity, a remarkable feat for a body so small and distant from the Sun. Other intriguing formations include bladed terrain, where sharp ridges of methane ice rise hundreds of meters, sculpted by sublimation and wind. These blades, found in regions like Tartarus Dorsa, are unlike anything seen elsewhere in the solar system, highlighting Pluto's unique environmental conditions. The interplay of ices, nitrogen, methane, and water creates a surface that is constantly reshaped by seasonal cycles as ices sublimate and redeposit, with Pluto's changing distance from the Sun. Studying Pluto's surface is crucial for understanding the evolution of icy worlds, both in our solar system and beyond. Its geological activity draws parallels to moons like Europa, Enceladus, and Triton, which also exhibit active surfaces driven by internal heat or tidal forces. However, Pluto's lack of a massive parent planet makes its activity particularly puzzling, as it relies on residual heat from its formation or radioactive decay rather than tidal heating. This makes Pluto a key case study for modeling how small bodies sustain geological processes over billions of years. Furthermore, the presence of organic compounds like tholins on the surface raises questions about the chemical complexity of the Kuiper Belt. While Pluto is too cold for life, these molecules are precursors to the chemistry that could lead to life on warmer worlds, making Pluto a stepping stone for astrobiology. By comparing Pluto's surface to Earth's or Mars's, scientists can better understand why some worlds remain geologically active while others become dormant, offering insights into the factors that shape planetary destinies. The diversity of Pluto's surface also underscores its role as a representative of the Kuiper Belt. Similar geological features may exist on other dwarf planets like Eris or Makemake, but Pluto's accessibility to new horizons has made it the best studied example. Its surface tells a story of a world shaped by both internal and external forces, from cryovolcanism to solar-driven sublimation, and studying it helps refine models of planetary geology. For instance, the convection in Sputnik Planitia provides a natural experiment for understanding how icy mantles behave under low gravity, a process relevant to icy exoplanets or moons. Pluto's surface is not just a frozen wasteland, it's a dynamic canvas that challenges our assumptions about what small distant worlds can achieve, pushing the boundaries of planetary science. Pluto's orbit and moons form a fascinating system that reveals the dynamic nature of the outer solar system. Pluto follows a highly elliptical 248-year orbit, ranging from 4.4 billion kilometers at its closest to the Sun, perihelion, to 7.4 billion kilometers at its farthest, aphelion. This eccentricity drives temperature swings from 240 to 218 degrees Celsius, influencing the sublimation and freezing of surface ices that create its cyclical atmosphere. Its orbit, tilted 17 degrees from the ecliptic plane, suggests gravitational influences from the early solar system, possibly tied to Neptune's migration. Pluto's orbit is stabilized by a 3.2 resonance with Neptune, meaning Pluto completes 2 orbits for every 3 of Neptune's, preventing collisions despite their intersecting paths. This resonance highlights the gravitational harmony of the Kuiper Belt, offering insights into its formation and dynamics. Pluto's largest moon, Charon, with a diameter of 1,212 kilometers, forms a unique binary system, as both orbit a shared center of gravity outside Pluto's surface. Observed by New Horizons in 2015, Charon's gray-cratered surface features a reddish polar cap, likely methane from Pluto's atmosphere turned into tholins. Tidally locked, the pair share a synchronized orbit 19,600 kilometers apart, possibly formed by a massive ancient collision. Pluto's 4 smaller moons, Styx, Nix, Kerberos, and Hydra, range from 10 to 55 kilometers and have irregular, icy surfaces. Their chaotic orbits suggest they are debris from the same collision, adding complexity to the system. The Pluto-Charon system is a microcosm of the Kuiper Belt's diversity, helping scientists understand how collisions shape small bodies. Organic compounds on Charon hint at the region's chemical richness, making Pluto a key to studying the outer solar system's evolution and its ancient secrets. Exploring Pluto has been a triumph of human curiosity and ingenuity, marking a historic milestone in our quest to understand the outer solar system. For decades, Pluto was a mystery, known only as a faint speck in telescopes, with limited details about its orbit, size, and moon, Charon. Its reclassification as a dwarf planet in 2006 sparked renewed interest, highlighting its role as a key Kuiper Belt object and fueling efforts to explore it directly. NASA's New Horizons mission, launched in 2006 and reaching Pluto in July 2015, transformed our understanding. The spacecraft's flyby revealed a dynamic world with the heart-shaped Sputnik Planitia, water ice mountains, and possible cryovolcanoes, proving Pluto's geological activity. It confirmed the atmosphere's layered hazes and cyclical nature, while observations of Charon and the smaller moons, Styx, Nix, Kerberos, and Hydra, unveiled a complex system, evidence of a past subsurface ocean and organic molecules like tholins, raised questions about Pluto's chemical complexity and its relevance to prebiotic chemistry. The mission's data, still yielding insights, has reshaped our view of Pluto and the Kuiper Belt, informing studies of icy worlds and exoplanets. New Horizons' later exploration of Arakoth in 2019 extended its legacy. Future missions, such as orbiters or landers, could further unravel Pluto's mysteries, exploring ongoing cryovolcanism or organic chemistry. The mission's success, driven by thousands of scientists and engineers, captured the public's imagination, with Pluto's heart-shaped plain becoming an icon of exploration. It reminds us that even the smallest worlds hold profound secrets, inspiring us to push the boundaries of discovery and dream of what lies beyond. Pluto, the farthest wanderer, as I fondly call it, is a beacon of wonder, its icy heart and fleeting atmosphere defying its small size and distant orbit. It challenges what we believe a world can be, reminding us of Earth's fragile uniqueness while showcasing resilience in the harshest conditions. As we analyze New Horizons' data and dream of future missions, Pluto calls us to explore the unknown. Could its ices whisper secrets of cosmic origins? Its story stirs the soul, urging us to embrace the cosmos's mysteries. Pluto teaches us a profound lesson. Like this tiny world, we navigate moments of isolation and change, yet find beauty and purpose in resilience. Its ability to endure inspires us to embrace our uniqueness and persist, shining brightly despite the odds. How can we, like Pluto, carve our own paths through life's vastness? As we gaze at this distant world, let its story move you to dream bigger and cherish existence's fragile beauty. So as we gaze upon this tiny world billions of kilometers away, let Pluto's story move you to dream bigger, to question deeper, and to cherish the fleeting, fragile beauty of existence. Drop your theory in the comments because we want to know what's spinning in your mind. We hope this video has been helpful to you. If you have anything to add or any video suggestions, please share them with us in the comments section. Like and share the video. Subscribe and follow us on our social media, whose links are in the description below. And remember, knowledge is an investment with inexhaustible returns.